Now we have set up eBGP peering and advertised a network using BGP. Now let's configure iBGP, so the peering within AS 65001, and we use the same neighbor command, except that we will be using loopback addresses within the autonomous systems 2222, which is router 2's loopback address. And remember that router 1 already knows this address because router 2 has already advertised it using OSPF. And the remote autonomous system is the same in this case, so 65001. This indicates that we are using iBGP, and we also want the loopback address as the source IP address, so one additional command is needed. Neighbor 2222 update-sorce loopback 0. So now the iBGP peering is not path dependent. So if this link between router 1 and router 2 fails or goes down for some reason, we can still maintain this neighbor relationship through router 3. And we use the same commands for router 3. So neighbor 3333 remote autonomous system 65001, and also the update-sorce command. Now if we had 10 routers in this AS, for example, we would have to configure 10 neighbors, because there is this iBGP split horizon rule, which says that if an iBGP router 2, for example, gets on NLRI from another BGP router 1, for example, so it does not forward it to any other iBGP router. So in this case, router 2 won't forward it to router 3, because an iBGP router always assumes that the other BGP router who he has got this route from, so R1 in this case, would forward the route to all other iBGP router. So that's why we need this full mesh topology within the autonomous system. So we need to issue separate neighbor command for every other router within the autonomous system. So this does not scale very well, obviously. So we could set up a route reflector, for example, to solve this problem. But we won't do that in this video. So we use this full mesh configuration. And I think we are done with router 1. So let's check our BGP neighbors. I'll show BGP IPv4 unicast summary, and the state of the iBGP neighbors are idle, which means that we haven't configured BGP on those routers. So we are just sending TCP SYNs to port 179. But since that port is closed on the remote router, we just get back a TCP reset. And one more thing, remember that with eBGP, the TTL value was set to 1, so the two peers had to be directly connected. With iBGP, we don't have such a restriction, so the initial TTL is 255, so we could peer with any router, even multiple hops away, and we should, because of the full mesh I mentioned before. if we see a number here, that's a good sign, because that means that we have received 4 prefixes in this case, and the BGP session is up. And now let's move on to router 2. On router 2, we have to set up one eBGP neighborship and 2 iBGP neighborship. So let's start with iBGP. For router BGP, the AS number 65001, neighbor 1111, remote AS is the same, so it's an iBGP session, and also the update-sorce command. And the same for router 3, so neighbor remote AS, which is the same, and also update-sorce loopback0. And the neighbor relationship with router 1 is established successfully. So router 2 should have received the routes from router 1. So let's check it. Do show IP BGP. Indeed, we have received every route from router 1. But if we check the routing table, or do show IP route, or do show IP route BGP, we can see that it is empty, and we don't have any route learned with BGP. And notice that this greater than sign is missing at the beginning of every row, except this one, and it says that R indicates that it is a RIP failure, which just simply means that this route is already in the routing table, because router 2 has already learned it with OSPF, which has an administrative distance of 110, while iBGP has an AD of 200, so the OSPF route is preferred. And the issue here is that the next hop address in this column is not reachable for router 2. So this 14.4 is router 4's address, and router 2 doesn't know that. Remember that on iBGP peer, router 1 in this case, doesn't change the next hop attribute while forwarding the NLRIs from an eBGP peer. So see, the next hop attribute is unchanged. To solve this issue, we could either redistribute this connected network into OSPF so that R2 could reach this network, so this 14.0/24, or a much better option if we change this next hop attribute in the update message. So on router 1, we enter the BGP configuration mode, and we issue one additional neighbor command. So neighbor 2222, and the next hop unchanged option is the default, what we have seen here. So let's change that to next hop self. And for the other neighbor as well. And I'm gonna restart the whole BGP process on router 1 to force router 1 to resend the advertisement. So clear IP BGP. So we could either do a hard reset or a soft reset. I'm gonna do a hard reset. Don't use this in a production network, but this is just a lab. So to speed things up, I do this. And let's check the routing table of router 2 again. Show IP BGP. And the next hop is changed. And now all routes got into the routing table. We'll show IP route BGP. And let's finish the configuration of router 2. So I use the next hop self here as well, on neighbor 1111. So router 2 will change the next hop in the attributes of the routes, which router 2 gets from router 7, so from autonomous system 65007. And finally, let's configure the other iBGP neighbor, so router 3, to establish the full mesh. On neighbor 3333, remote AS is the same. Update-sorce loopback 0, and we change the next hop attribute. And let's set up the eBGP peering with router 7. So neighbor 10.027.7, which is our 7th address of G00, and the remote AS is 65,007, and the neighbor relationship has been established. Let's check the BGP table to show IP BGP, and many things have changed. For example, previously to get to R7, we used this very long AS path. So we went to AS 65004 and to 65005, 6, and finally 7. Now it's a single hop, and to reach router 5, we have 2 paths to choose from. We could either go to AS 65007, which is router 7, and then to router 6 and to router 5 to reach AS 65005, or we could go through router 1, then using AS 65004 and reach 65005, and we prefer this path through router 1. So why is that? This is because if the weight and the local preference are not defined, the deciding attribute is the length of this AS path string. So in this row, we have to go through 2 autonomous systems, while in the other case, we have 3 autonomous systems to go through, and 2 is less than 3, so this one is preferred. And now let's advertise router 2's loopback address as well with the network command, and the mask is /32, and we move on to router 3, router BGP 65001, And here we have two iBGP neighbors. So let's start with those. Neighbor 1111. Remote AS is the same. We use the update-sorce command and the next hop self as well. And the other neighbor, router 2, and we are done with iBGP. We also have two eBGP peers, neighbor 10.0.34.4, which is the IP address of router 4's G02 interface, and the remote AS is 65,004, and the other neighbor 10.0.35.5, which is router 5's IP address of interface G0/1, and the remote AS is 65,005. And now we should have 4 BGP neighbors. So let's check that to show BGP IPv4 unicast summary, and every neighbor relationship is established and up. So let's advertise the loopback address using the network command. And we are done. Now let's verify what we have configured. So on router 6, for example, we should have a route to the loopbacks of all routers in this AS 65001. So let's check that. Show IP BGP, and we do. And we should have a full connectivity. And we should be able to ping, let's choose one, or router 2, for example. The loopback address is 2222. We ping using the source IP address of loopback 0, and the ping is successful.